So welcome back. This is part 3 in my series on an engineer's approach to understanding climate change. And I encourage you to look at parts 1 and 2 where I kind of lay out what I'm doing in the series and my major questions about climate change that I was hoping to get answered as I bring you along on my journey to try and get down into a little bit more of the facts behind climate change from an engineering perspective, to see what the data is. And I explain how there are some things that engineering-wise didn't really make a lot of sense to me in this whole climate change discussion. So I'm trying to figure out some of the data, and I even have developed a software simulator, which I introduce in part 2. And in this part, we're going to look at the results of that software simulator. And we're also going to take a little closer look at individual device bias to see if maybe some of the temperature measurement devices might be biased in one direction that might throw off the total measurement. So here is the software that I developed. And basically, it's going to simulate 1,000 devices and simulate taking 365 separate readings of all 1,000 devices and averaging all of those together to try and decide if you can get an average number for the year that is close to what the measured value should be, which in our case is 52 Fahrenheit. So what I'm going to do is I'll press the sample devices button, and it will populate this interface with a bunch of data that will help us decide. And again, I've got over here, I've got a sample of 1 day's worth of readings from all 1,000 devices, and I've just printed it out just so I can verify that they're fairly random numbers between 50 and 54. So I've got, you can see on the top, device 0 all the way up to device 999. And as you can see, the numbers are fairly random between 50 and 54. So I've got just by looking this, I've got a pretty good feeling that these are truly random numbers between 50 and 54. So what I did just to verify that is I took all those numbers and put them into this top chart, which is a histogram that tells you for each range of numbers, how many occurrences are there. And if they're truly random, then I should have a fairly flat number of occurrences for each range of numbers. So for example, this is like from 50 to 50.2 degrees, and I should have about the same number of occurrences in that range as I do in every other range. And as you can see here, it's not perfectly flat, but usually it's about 50 to 60. And you can see it kind of averages to a flat number of occurrences. So what this tells me is I do have a fairly random distribution of readings between 50 and 54. And the proof will be in whether these, how all these average out. And then on the bottom here, what I've done is I have taken, again, I've got 365 averages. And what I'm doing is I'm taking those 365 averages of each day's readings and putting them into another histogram to see what the averages look like. Not the individual readings, but the daily averages. And you can see here, while here I was between 50 and 54, here the averages are between 51.88 or 51.8, something like that, is a low, and 52.1 as a high. So the averages are now quite a bit better than the actual readings. And up here I put the maximum daily error, which is these are showing one error they show it to be 51.88 when the actual one is 52, so we'll just take the difference. So you can see the errors are like plus or minus 0.1 degrees Fahrenheit. So you can see instead of plus or minus 2 degrees, now the averages are plus or minus 0.1. So interesting. again, we've used some very inaccurate plus or minus 2 degrees, and now we're getting minimum and maximum errors of about plus or minus 0.1. Now, if I take all of those daily ones and average them together so I get one final average number for the year, I plot that right here. And you can see the answer is, if I took all of those averages of the averages, I get 51.9994, where the actual is 52. So you can see, wow, I've got a very accurate, I mean, the difference is 0.0006 degrees Fahrenheit. So I'm using some inaccurate devices under the assumption they are uniformly random, which is a big assumption, which may not be legitimate. But at least to prove this theory, if you use uniformly random numbers, you can get a very accurate number. Now, what I can do is I can hit this again and try another set of 365 samples of 1,000 devices. And the answer is, again, very accurate. And you can see my maximum errors are plus or minus about 0.1 again. And here is a little less accurate, but still it's 0.002 degrees accurate. And I do it again, 0.001 off. Again, theoretically, you can get some very accurate readings if you average the averages of a lot of devices that are themselves uniformly random devices. Now, this means they don't have any bias. So, for example, let's say half of your 1,000 devices were all one model that tended to read a half a degree high. Then, of course, this would no longer apply. You'd be off by half a degree in your final answer. Now, what I can also do is I can change this accuracy to be some really wildly inaccurate devices, make them accuracy of plus or minus 20 degrees Fahrenheit, and run it again, and you can see now my maximum errors are about 1 degree, even though it's a plus or minus 20 degrees. Still, it's very accurate relative to that, but the yearly average is still very accurate. You're 52.01, so you're 0.01 accurate versus the 52. And I do again, 51.99, 52.03. So again, it's less than 1/10 of a degree, even though I'm widely off in each of the devices' accuracies. But again, it's because all of the highs and all of the lows are kind of canceling each other out, because it's uniformly distributed. So these numbers here are canceling out these numbers here. Now, what I can also do is put a bias, which means, let's say each device is biased to read 1 degree high, and you can see now it doesn't work anymore. Now I'm biased by 52 versus 53, and my numbers are reading high because there's a bias in the reading. So the question is, how much bias is in the devices? Are they uniformly random, or do they have some bias that ends up making this number not what we are expecting? So again, after doing this exercise, I came to the interesting conclusion that to the extent that these are uniformly random devices, you can get some very accurate results with inaccurate devices. So my next question was, okay, we assumed that the devices were randomly inaccurate. What about actual device accuracy? What can we find about the actual accuracy of devices in the real world? It was difficult. I tried to do some searches to find discussions of actual device accuracy. It's real difficult, and that's got me kind of scratching my head. Why is it so difficult to find discussions of climate device accuracy? Maybe I just didn't do it right, but I did find a paper from 2004 by Lynn and Hubbard, and I believe they're University of Nebraska, and it was called Sensor and Electronic Biases / Errors in Air Temperature Measurements in Common Weather Station Networks, which seems to be right exactly what I was looking for. And it says the biases of 4 commonly used air temperature sensors are examined and detailed. And their conclusion was it was found that regardless of microclimate effect, sensor and electronic errors in air temperature measures can be larger than those given in the sensor manufacturer specifications. So this says that, yeah, what you read in the manufacturer specs may not apply on actual devices. And here is some of their results. They did 4 typical climate measuring devices and looked at their accuracy. And the results are kind of complicated. They showed that depending on the device, there are different components in the device and different, like resistor accuracies, data loggers, and a bunch of different components have different accuracies. And these charts show, based on temperature, what's the errors in degrees C. And you can see for most of them, as you get into the outside ranges of temperatures, the accuracies can bounce around quite a bit. And here we have on the bottom left a minus 1.2 degrees centigrade error for some components. So basically what this says is, depending on temperature, like we saw before, your accuracy can vary, but it can also be not what you expect it to be from the manufacturer's specifications. Now, again, this wasn't real clear on what the overall answer was, other than you can get some variations in accuracy up to 0.4, 0.5. Here's 0.6, 0.4. So it just brings a little bit more question about actual device performance compared to what the specifications are. So in my looking around the internet to see if there are devices that are really, really accurate, and to my surprise, there weren't many, but I did find a device, and this was called a reference thermometer, and it was at a company called Thermoworks, thermoworks.com, and I have absolutely no relation whatsoever to them. I'm just mentioning that they have this reference thermometer, and I believe it costs around $300 thereabouts. And actually, I was thinking of buying one, even though I don't need it, because it's such a nice idea to have a highly accurate device. This thing is accurate to plus or minus 0.1 degrees Fahrenheit accuracy, and that includes the probe and the internal device. And if you look at their accuracy claim, it's plus or minus 0.1 degree Fahrenheit, which is 0.05 degrees centigrade, from minus 22 to plus 302 degrees Fahrenheit. So that was really surprising to me. A lot of devices don't get to that accuracy, a lot of commercial devices, unless I think you spend, $500 or $1,000. So again, that brings up another issue that they mentioned in the National Weather Service document, and that's not about the device itself, it's about where you cite it, where you put it. So what I did is I happened to be looking around one of the major weather websites where they have private citizens or just public participants who buy a weather station, and they tie it into this major website reporting mechanism. And I found near me was a fire station where they bought a weather station, and they hooked it up to this temperature website, and they become a recording. They input to the global recording for this website. In the document from National Weather Service, we mentioned before citing, and one of the requirements in that document, section 3.1, air temperature measurement, it requires that you install the temperature instrument according to the following standards. Number 1, over level terrain, earth or sod, typical of the area around the station, and at least 100 feet from any extensive concrete or paved surface. And again, I looked at this local temperature station, and they mentioned the model name of this recording device. And here's a photo of the installation. It's mounted on the side of the building on a pole. I'm guessing this is probably 20 or 15 or 20 feet off the ground. And I looked at the manufacturer's data on the accuracy, and this is about $1,000 weather station, very high end. And according to the manufacturer, if I read it correctly, it's plus or minus 0.5 degrees accuracy for temperature measurements. And you can see they've got this mounted about 15, 20 feet from the ground, and in the ground is this big asphalt parking lot. So it's nowhere near the requirement of 100 feet from a paved surface, and you can see why that's a requirement. I mean, obviously, as this heats up from the sun, if you've ever, touched a hot asphalt parking lot with your hand in the summer, it generates a lot of heat. So it's kind of a little bit funny that they've got a 0.5 degree accurate device that is mounted 15 feet away from a paved asphalt parking lot. So it just raises the rational question you have to ask yourself: to what extent is this common in device measurements that are used for climate or any other measurement, right? I mean, it's kind of tough to make sure that your device is totally free from anything that might, you've got a red brick building that's emitting heat, and you got to ask the question at least. And that, even though you can have a very highly accurate reading from 1,000 devices that are randomly distributed with accuracy, what about those that are clearly going to have some sort of bias? I mean, that's got to be a question in your brain. What's the actual answer here? So that's just one more thing that weighs into the equation. So again, as far as accuracy, from what I found, accuracy can be vastly improved by increasing measurements, assuming a uniformly random or better distribution of errors without biases. And the question becomes, in the real world, what are the actual accuracies and biases of the recording networks used for the climate measurements? And I don't know. And honestly, I don't know if you can put a number to it. I mean, can you go to the existing climate measurement networks and say, okay, tell us how accurate what are the error bars on the accuracy of your readings based on these things that we just addressed, the sighting and the individual biases of the devices. Again, I don't know the answer. It may be that this is something there's no need to worry about it, but it just, as an engineer, it's a question that I feel needs to be answered, at least for me to feel confident in the results. So again, that's kind of my thoughts about accuracy. Again, I don't have the answer, but this is kind of another step in my journey. But I did learn that at least some of my concerns were not realistic, assuming you have uniformly random biases or random errors. Again, if you like this, please hit like, subscribe to this. Otherwise, take care and thank you and have a good day.